Hello viewers, welcome to CEC Gurukul lectures. In my previous lecture, I had introduced to you elements of symmetry in a molecule, in which we had discussed the plane of symmetry and the center of symmetry. That is, a plane of symmetry is a plane which divides the molecule into two equal halves so that one half is superimposable on the other half and the molecule is optically inactive in spite of having chiral carbons. The second element of symmetry which I discussed was center of symmetry. A center of symmetry is a point through which lines joining identical groups intersect each other, and the identical groups are equidistant from the center. Then we say that the molecule has center of symmetry. And here also molecule will be optically inactive in spite of having chiral carbons, because there is element of symmetry, and one half, the optical rotation due to one half of the molecule will be cancelled by the other half, because the optical rotation due to these two chiral carbons or due to these two parts will be equal in magnitude but will be opposite to each other, so the net result will be 0. So let us now continue from there and see that what are the other elements of symmetry which can make a molecule optically inactive. We have a simple or a proper axis of symmetry which is denoted by Cn. This is an imaginary line which is passing through the molecule in such a way that when molecule is rotated about it by an angle of 360 by n, an arrangement indistinguishable from the original is obtained. So what is the operation here, symmetry operation that we are carrying out here? It is the rotation. That is, when we rotate the molecule, it will change into the other structure which is indistinguishable from the other. So what we find is that this is known as Cn symmetry, or this is known as, and the operation that we are going to carry out, we are going to rotate the molecule by 360 degrees, and then we are going to see how many times will a indistinguishable structure be obtained. If it is obtained 2 times, we say it has n-fold symmetry, axis of symmetry. If it is repeated 3 times, the structure, the indistinguishable structure on an equivalent structure, we will say the symmetry is 3 times. That is, the molecule will occur 3 times. And if it is occurring 4 times, then we will say the molecule is having 4-fold axis of symmetry. So now let us demonstrate. So this axis is called a simple axis of symmetry or n-fold axis of symmetry, and as I have already said, this is designated as Cn, and the operation is called the Cn operation. So what we have to remember here is that what is Cn here? Cn here is the one complete rotation, that is by 360 divided by n, where n is the rotation of axis, that is whether we are rotating the molecule around the axis and we are getting the same configuration 1 time, 2 times or 3 times. And the rotation about this axis by an angle of 360 by n will convert the molecule into its identical twin. So what I mean here is that if n is equal to 1, that means the angle of rotation will be 360. If n is equal to 2, that means angle of rotation will be 360 divided by 2. If n is equal to 3, that means the angle of rotation is 360 by n, where n is the order of rotation, and if n is equal to 4, that means the angle of rotation will be 360 by 4. Now what do we mean by this? This means when the order of symmetry is 2, that is also called as n-fold axis of symmetry, which is when the order of symmetry is 2 of the symmetry axis Cn, then we say that when we are rotating the molecule by 360 divided by 2, that means this molecule will have identical configuration or equivalent configuration twice. When we say it is the value of n is 3, that means when we have rotated after every 120 degree rotation, we will get the same configuration of the molecule or the identical configuration. And if n is equal to 4, that means when we are rotating the molecule by 360 degrees, then we will get 4 times equivalent configurations. That is, after rotating the molecule by 90 degrees, we will get an equivalent rotation. Then we will rotate it by another 90. That means by after 180, we will get a equivalent structure. So here what I want to explain, what I had done in my previous lecture also, that if we take an example of molecule, then what we find that the order of rotation axis is 2. And what is the symmetry element here? C2 axis. Now we are going to carry out 2 operations, that is C21 operation and C22 operation. And here this E is known as identity operation. What is this identity operation? Identity operation is the sequence of operations which brings the molecule back to its original configuration. So supposing I say that I am rotating the molecule by 180 degrees, I will get a equivalent structure, and then I rotate it by another 180, because what we are saying, the order of rotation of axis is 2. So if the order of rotation of axis is 2, that means the Cn value will be 360 divided by 2. That means it will be 180. That means after we've rotated 180, we will get one configuration which is equivalent to the original. And then when we rotate it by another 180 degrees, we will come back to the original configuration. So we will have to carry out 2 C2, that is 2 operations. That is, in one operation we are getting, that is when I rotate this by molecule by 100, this is the axis which is passing through oxygen atom, bisecting the water molecule. We find that when we rotate this axis here, we will get an equivalent structure. That is, we are flipping these 2 groups by 180 degrees. That means 2 will go here, 1 will come here. So we are getting an equivalent structure. Now we flip this again by 180, and what we find, that we will get a structure which is similar to original. That is, 1 is on the left hand side, here also 1 is on the left hand side, here 2 is on the right hand side, here 2 is on the right hand side. So this molecule has 2-fold axis of symmetry. That is, after every 180 degrees rotation, while we are rotating the molecule by 360, we will get an equivalent structure, or we will get back to the original structure. So this is what I am repeating again here. In case the identical structures result twice on rotation of the molecule by 360, the axis is called 2-fold axis of symmetry, and when identical structures repeat 3 times, it is called 3-fold axis of symmetry. For this we can take a simple example of BF3. In BF3 we know that B is sp2 hybridized, and since it is sp2 hybridized, it will have a planar structure. And now when we rotate the molecule by 120, what we'll find is that we are getting a identical structure. We rotate it again by 120, we'll get another identical structure, and then when we go rotated by another 120 degrees, we will get the original structure. So we say when we have threefold axis of symmetry, what we mean here is that the molecule will occur 3 times in the indistinguishable or in the equivalent configurations. Now here again you can visualize, I have taken an example of a ceiling fan, and here again I have demonstrated that it has threefold axis of symmetry. That is, this we can imagine that supposing I say this was a molecule of BF3. So this is boron, this is 1F, this is 1F, this is 1F. This has a planar structure and the bond angle here is 120 degrees. So now when we make a rotation of 360 degrees, what we find that after the rotation of 120 degrees, this will come here, this blade will come here, this blade will go here, and this blade will come here. So we are getting an equivalent structure. Now we rotate it again by 120. So that means again the blades will interchange, and after 360 we will get the original structure. So that means the blades will appear 3 times at equivalent positions on a single rotation of 360 degrees. Now let us take another example here, and this example is that of 1,3,1,2,3 dimethyl cyclobutane. Now this again has a twofold axis of symmetry. Why does this has a twofold axis of symmetry? But because here the identical parts are on the opposite side of the molecule. That is, this is here and then we have it here on the opposite side. So now if I say that I make and rotate the molecule by 90 degrees, we will get an opposite configuration. What I mean here is that this H, which is this, okay, this H will be, this H here will be here, that is here we'll have both the H's, H and H, and this CH3H will go here. But what we want, so that means we'll have to make another interchange of 90 degrees. So what, in simple language we can say that when the two groups are on the opposite side, we have flipped the molecule by 180 degrees. So when we flip the molecule by 180 degrees, we get the same configuration. So that means we have rotated around the axis of symmetry by 180 degrees to get back to the original configuration. So that means, so see now if I had rotated this by 90, that is, this is 90 degrees to the axis. So this would have been H and this would have been H, this would have been CH3 and this would have been H. That means we are at the opposite configuration. So that means we'll have to make another interchange of 90 degrees. That means we'll have to rotate the molecule in anti-clockwise direction by 180 degrees when we will get the original molecule. So this molecule, that is 1,3-dimethyl cyclobutane, has twofold axis of symmetry. Now we have the last element of symmetry which can make a molecule optically inactive, is alternating or improper axis of symmetry. So this is called as rotation reflection axis. Please remember, simple axis of symmetry is a rotation axis, that is, we are rotating the molecule around the axis. Whereas when we are talking of rotation reflection axis, what we have to remember here is we say that a molecule will possess an alternating axis of symmetry, which is Sn, if the rotation of the molecule about the axis by 360 by n followed by reflection through a plane perpendicular to this axis produces a structure which cannot be distinguished from the original, then we will say that the molecule has alternating or improper axis of symmetry. What I mean here is, that is, first we will rotate the molecule around this axis by 360 divided by n, which is the order of rotation. And after rotating this, now we will view the molecule in such a manner, that is, we will place a mirror perpendicular to this axis of rotation, and then we will view the reflection. And if the reflection which is produced cannot be distinguished from the original structure, then we say that the molecule has an alternating or improper axis of symmetry. Now let us take an example of 1,2,3,4 tetramethyl cyclobutane. And what we find, that when we rotate this molecule by 90 degrees about the axis passing through the center of the molecule and then reflected in a mirror perpendicular to this axis, an arrangement superimposable on the original object will be obtained, or original molecule will be obtained, that is, it will be indistinguishable. So as you can see on your screens, this is the structure of the molecule, which is 1,2,3,4 tetramethyl cyclobutane. Now what we do, we rotate this molecule around this axis by 90 degrees. So when we rotate it by 90 degrees, this group will come here, that is HCH3, and this group will go here. This has come here. This group will occupy the position 4, and 4 will occupy the position 1. Now what we have to do is, after rotating it by 90 degrees on this axis, we will place a mirror here which is perpendicular to the axis, that this is the axis, we've placed the mirror here. So axis of rotation, and we've placed the mirror here, this is at 90 degrees to it. Now let us view the molecule. Then when we view the molecule, we find that the structure of this molecule is identical to the original structure. So we say this molecule has alternating axis of symmetry, and this will be superimposable on its original molecule. The mirror images, this object, this molecule which we are getting after rotation and reflection to a mirror plane perpendicular to the axis of rotation, is indistinguishable from the original molecule. So this molecule will be again optically inactive due to the alternating axis of symmetry. Now the question arises, what is more important, molecular asymmetry and dysmetry? Both are the causes of chirality. That is, if a molecule is asymmetric, that is, if it is having a one chiral carbon and no plane of symmetry, no element of symmetry, then we will say that molecule is optically active. But if a molecule is having more than two or more than two chiral carbon atoms, then in that case molecule should be dysymmetric. That is, it should not have a plane of symmetry, center of symmetry, simple axis of symmetry, or alternating axis of symmetry to be optically active. So this is what I have shown here, that if a molecule has a single chiral carbon, that is this chiral carbon, and this carbon is now attached to 4 different groups, so we also call it as stereogenic carbon. So as a result of this carbon, this molecule becomes chiral, and we say this molecule is chiral and this carbon is asymmetric, due to which butane to amine is optically active and will exist as an enantiomeric pair, one of which will be dextrorotatory and the other will be levorotatory. But now if the molecule has 2 or more than 2 chiral carbons, then it should not have a plane of symmetry, center of symmetry, alternating axis of symmetry or simple axis of symmetry. Then only molecule will be optically active. That means all asymmetric molecules are dysymmetric. That is, if a molecule is asymmetric, it does not have a plane or either of the elements of symmetry. That means the molecule will be dysymmetric. But all dysymmetric molecules are not asymmetric. But both of these will show optical activity and will be chiral. So to avoid confusion, that is where we will use the term asymmetric, where we will use the term dysymmetric, we simply use the word that the molecule is chiral. So to be optically active, molecule has to be chiral. That is, it should be non-superimposable on its mirror image. Now let us take an example of allenes which do not have a chiral carbon. That is, we see that due to sp hybridization in allenes, the central carbon atom which forms 2 pi bonds, those pi bonds are perpendicular to each other, and the 2 groups attached to the terminal carbon atoms are also orthogonal. What I mean by saying orthogonal here, that is, they are also perpendicular to each other, and due to this arrangement, the molecule of allene is devoid of any element of symmetry. That is, it will not have a plane of symmetry, it will not have a center of symmetry, neither axis of symmetry or the alternating axis of symmetry, the simple axis of symmetry or alternating axis of symmetry. See, what we mean here is that this carbon here is sp hybridized, and I have taken here the example of 1,3-diethyl, 1,2,3,1,3-diethyl, 1,3-dimethyl allene. So when we look into this structure, we find that this carbon is sp hybridized. So if it is sp hybridized, that means that 2 pi bonds which are being formed are at right angles to each other. So when we have these pi bonds right angles to each other, what we find that these terminal groups are also at right angles to each other, and when they are right angles to each other, they will form non-superimposable mirror images of each other and will be optically active. So that means non-dissymmetric molecules will be all. That means dissymmetric molecules will be optically active. Now the third thing that we have to take into consideration, that if we have a non-disymmetric molecule, that is, which possesses a plane of symmetry, a center of symmetry, alternating axis of symmetry or simple axis of symmetry, then those molecules will be achiral and optically inactive. So what we conclude from this lecture is that the necessary and the sufficient condition for a molecule to be optically active is that it must be dissymmetric. That is, if it has chiral carbons in it, if it has 1 chiral carbon, molecule will be optically active. If it has 2 or 3 or 2 or more chiral carbons, then molecule should not have any element of symmetry. And third point that we have to keep in mind is that there are certain molecules which do not have chiral carbons but are still optically active because they do not have element of symmetry. Therefore, we say the necessary and sufficient condition for a compound to exhibit enantiomerism is that they should possess chirality or dissymmetry rather than asymmetry. Thank you.